This is the second video on algebraic geometry. If you're joining me from the first video, thanks for watching. The first thing we need to talk about is the affine space. This is the space in which we'll be working for the first part of these videos. The affine space is just a collection of points, all of the points, very similar to a vector space, if you know what a vector space is, that look like this. So these are n-tuples, a1, a2, an, right? And these are inside this affine space within dimensions. Now, a really important question worth clarifying is what's the difference between an affine space and a vector space? And for that, I'm going to draw a figure here that I did not come up with, but it's worth going over. Here I have the vector space R3. And when we think about R3 as a vector space, what we're assuming is that we are starting at the origin, 0, 0, 0, or 0i plus 0j plus 0k, or 0 with a little vector sign over the top of it, whatever you want to call it, and we're kind of picking a point in here somewhere, and we're sort of drawing an arrow to that point. Okay? And the idea that's expressed with a vector space is really the magnitude and the direction, that you would face a certain direction and hit that point if you were traveling, say, one time unit. If we're considering this vector space and we wanted to, say, find a subspace of this vector space, one thing we could do is take a plane that slices through the origin. So for instance, what I'm going to do is I'm going to take this plane that lies along the z and y axes and passes through the point 0, 0, 0, or through the vector 0, I should say, not point. This is a subspace. This is a subspace of R3 that's isomorphic to R squared. So this is a subspace that's isomorphic to R squared. Okay? Now, if I were to take the plane that, say, went through this point instead, and was parallel to the plane that I just drew, I'm going to try to do this neatly. Right, so hopefully you can see I have two different planes here. One of them passes through the 0 vector and one of them does not. This plane looks exactly like this plane, but it is not a subspace because it does not have the 0 vector. This plane would be the perfect example of an affine space. We would call this AR squared. So to clarify, the difference between an affine space and a vector space is that in a vector space, the origin is really from where all of your vectors come. In an affine space, you can move origins around as you like. The second thing to note is that we're working in the polynomial ring A. I'll call this ring A throughout the rest of these videos, I believe. And an example of this, an example of a polynomial that would be in one of these rings looks like this. Basically, we say A, and we have n indeterminants. And these are polynomials that use these indeterminants. So here's an example. 1 plus x squared minus x1 plus x3, x4 squared. This is an element of this polynomial ring. The first important idea of algebraic geometry is the zero set. We take a set T of the ring A, and we try to establish a set of points in the affine space where all the functions in T are 0. Now I've drawn pretty crappily this graph of several functions, f, g, h, and j, and I'm pretending for a moment that those are the only functions in my ring. And these hit zeros at P1, P2, P3, and P4, and I'm pretending for a moment that those are the only zeros in my affine space. Of course, these are completely stupid assumptions, but it's easier to work with smaller sets to understand what's going on. So we're going to try to construct the zero set for each of these little subsets of functions that I've listed here on the left. We'll start with z of t. The question I'm asking myself is which points of P1, P2, P3, and P4 do all of f, g, h, and j hit a 0? And I can see the only point for which that's true is P4, I'm sorry. Notice that I'm listing points in the affine space. Again, let's try U. Now I'm looking for common zeros between f, g, and h, right? Which points of P1, P2, P3, P4 are 0 for all of f, g, and h? Well, f has zeros at P1, P2, P3, P4, G has zeros at P2, P3, P4, and H has zeros at P3 and P4. So I have P3 and P4. Next, I look for the zero set of the set V, which contains f and g. Again, f is 0 at P1, P2, P3, and P4, and g is 0 at P2, P3, and P4. So I have the set P2, P3, and P4. Those are the common zeros for these two functions. And lastly, the zero set for the set W of the function just f is all of P1, P2, P3, and P4. Now obviously I've designed this in a way to demonstrate something very special about the inclusions of these sets. Notably, T contains U, which contains V, which contains W. F is in here, G and F are in here, F, G, and H are in here. But when I look for my zero sets, what I see is that the inclusion reverses, right? Z of t is contained in Z of u, is contained in Z of v, is contained in Z of w. This is another example of the reverse inclusion that we discussed in the last video. And that will appear as a theme throughout some of these videos. And naturally this makes sense because the larger the set, the more constrictive it is. The more I'm requiring from the functions, from the points that can be common zeros, right? And the smaller the set of functions, the less I'm requiring, so it can be larger. This second concept that is important in algebraic geometry is the ideal. The ideal is introduced in a different way in algebraic geometry than it is in ring theory, but it's very much a similar idea. The ideal in algebraic geometry is really a function of a subset of the affine space. So here we have I of u, where u is a subset of the affine space, and what we're doing is we're looking for functions inside the ring of polynomials that are all 0 on every point in that set. Now, before I go on with this example that we did with the zero sets, what I want to point out, and this is kind of an abusive notation, is that you can think of z as a function from the affine space to the ring of polynomials. You take some chunk from the affine space. I'm so sorry. Let me back this up here. This is backwards. So the thing that I want to think about is that the function z can be thought of, meaning this zero set up here, can be thought of as a function from some set inside the polynomial ring to the affine space. In other words, I'm taking functions and I'm getting out some subset of the affine space, whereas I, the ideal, can be thought of as acting on the affine space and giving me back some subset of functions, which happens to be an ideal. So we'll use this same idea, and instead of looking at functions on the left, we're going to look at sets of points. So again, we're going to assume that the only functions we have to play with are f, g, h, and j, and the only zeros we have to play with are p1, p2, p3, and p4. Now, if we're trying to find remember that we're getting back functions here from a set of points, so we're trying to find the ideal that gives us zeros for all of p1, p2, p3, and p4. The only function that works for, as you can see, is f. So this is just f. For y, we're looking for functions that are 0 on p2, p3, and p4. That's g and f. And for z, we're looking for functions that are 0 on p3 and p4. That's f, g, and h. Again, we have this lovely reverse inclusion. Y is included in x, and z is included in y, as you can see here. And that forces the reverse inclusion. The ideal of the points in x is included in the ideal of the points in y is included in the ideal of the points in z. One final thing to note here is that if we have the ideal of a union of subsets, what we actually are doing is intersecting the ideals of the respective subsets. Again, if these are not equal, this over here has to be a little bit more constrictive than either IU or IV. So this isn't very surprising.